Hi, everyone. Today, we're finally going to go over APL, which is the only array-based programming language we have that's part of the competition. And as you can see, I finally figured out how to put a virtual background of the programming language logo behind me. So hopefully I'll continue doing that for all of our videos. So just a few housekeeping items. First, the other APL lead for the Paradigm conference, Ria Delgado, is unable to join me today. So I'm going to be doing this first video by myself, but in the future, she will be joining us for our videos. Secondly, for most of the other videos, what we're using is a replicate environment. However, because of APL's very sort of out there symbols, we can't use a replicate environment very easily. So we're going to use the dialog environment that's provided by Dialog, which is also just a much better alternative to what replicate provides anyway. And it's very easy to get started with. So we'll put instructions for how to set it up and install it in our written curriculum. But for now, we're just going to dive right in and see some of the basics of APL. And just so you know, this is a sort of file that's been preloaded with several variables, just so we can access those variables without having to type them out, because that's one of the downsides when you start using an array-based programming language in the very beginning. When you're not very savvy at manipulating arrays, there tends to be a lot of typing out things. Okay, so with that said, we're just going to dive right in. Now, I know we marketed APL on our website as almost programming with Egyptian hieroglyphics. And as you can see at the top bar here, where there's all these different symbols that have meaning in APL, that is definitely true. But for our very simple operations, they do tend to share the same symbols. So for example, if I want to add two numbers together, I just use a plus sign. The same thing if I want to subtract two numbers. Now, to access symbols in APL, we use a sort of specific set of key sequences. And we can see that when we want to type a multiply sign, because unlike in most other programming languages, multiplication isn't represented by the star operation. It's represented by this X. So to get there, we have to do a backtick dash, and that gives us the multiplication operation. So 10 times 10 gives me 100. That star, in case you were wondering, is actually exponentiation. So this is 10 squared. And the same thing holds for division. Backtick equals gives us a division sign. And so there you go. There are your very simple operations in APL. Now, I think this is important to get out of the way first, though. So let me try doing this. 80 minus 80 minus 80, and I want you to predict what that will return. Okay, so you might be very surprised by this. If you are used to essentially any other programming language, you would predict minus 80 because 80 minus 80 is 0 and 0 minus 80 is minus 80. But APL does application of any function, any operation from right to left. So that means that we evaluate this segment of what we put in first. 80 minus 80 is 0, and then 80 minus 0 is 80. So just to show you how APL evaluates this, by default, it evaluates it by nesting parentheses on the right-hand side, like that. And it also doesn't have any sort of precedence difference in operations. So 10 plus 10 times 100, or 5. The 10 times 5 won't be done first. Instead, oh, sorry, in this case, the 10 times 5 will be done first because I put it on the right. What I meant to do was this. In this case, the 10 times 5 won't be done first, but the 5 plus 10 will be done first, multiplied by the 10 to get 150. So that's very counterintuitive, but in some sense, it does make things simpler because we don't have to reason about any different precedence levels. Everything just happens from right to left. So the next thing that we're going to look at is assigning variables. So again, assignment of variables happens with a specific operator. In this case, it is this arrow operator here, which we get by doing backtick, left bracket, like that. And so I can create a variable called years. And I'll make this capital because we already have one defined years that we're going to use later. And let's see, 2005, 2006, 2007, 2008. So before I press enter, I just want to go over what I did here. I created a variable called years. I used, oops, I accidentally opened another window. Sorry about that. So I created a variable called years, and I'm putting this array into it. So in other programming languages, we expect arrays to sort of be delineated with brackets and commas in between each element. But APL is, like I mentioned, an array-based programming language. So it simply takes any sequence of characters with a space in between them to be an array. So we don't have to do any of this. It knows that we mean an array because arrays are the fundamental unit with which you program an APL. They're sort of like the atomic unit. So now I just assigned this value into the variable years. You can think of this arrow as meaning something roughly like gets this value. So years gets the value of that array. Oh, and I accidentally double clicked it again. And so now when I type years in to see what's been stored in it, I get that array back. So for right now, I'm going to point you to two other arrays that we have loaded into our environment, price and quantity, which we can think of as representing maybe some items in a grocery store. Now, what we can do is we can naturally do operations on arrays in APL. So we can just add these two arrays together with the same plus operator. And APL knows that since these arrays have the same amount of elements in them, it just wants to add each element together. So the 6 and the 2 become an 8, the 4.2 and a 6.3 become a 10.2, et cetera, et cetera, et cetera. And this works for all of our basic operations. So we can multiply them, and we see that each sort of constituent element gets multiplied together. Again, the 6 and the 2 go to the 12, and the same thing happens for all the other elements. And just to sort of make sure that this works, we can do this for both division and subtraction. And so this is all that we're doing. We're doing an element-wise operation between the two elements. Now, we can also do something a little bit more complicated. For example, in this case, we just have a scalar, but we're combining it with this array over here. And how we're doing that is we're broadcasting the plus 10 across every element in the array price. So a plus 10 of 6 becomes 16, a plus 10 with 4.2 becomes 14.2, a plus 10 with 1.5 becomes 11.5, and et cetera. So you can think of on the back end, APL is recognizing that we can't actually do an operation between elements with these two different shapes. One of these is an array with multiple elements, one is just a scalar. So it converts this sort of 10 scalar because it knows what we really mean is adding it to each element. It almost converts that sort of scalar into a list, an array with the same amount of elements, and then it does the same logic as before. So that's how you can sort of think about this happening. And once again, this works with all our basic operations. So now what we're doing is we're mapping this times 100 operation across every element in our original list. So that is all of the sort of simple operations in APL very quickly. And you'll notice that they naturally vectorize. And that's just another way of saying that they are built specifically to work with arrays of different arrays that have multiple dimensions. And so here are two other sort of arrays that we can access in APL. In this case, we have an array called forecast, which is a array with 2 dimensions because we have rows and columns, and array of actual, which also has rows and columns. And you can think of these as predicting the output of maybe some manufacturing process for different conveyor belts in that manufacturing process over different months. And so we have an array of forecasted predictions and array of actual predictions. So just to show you again, since these two things have the same shape, our inbuilt multiplication, addition, subtraction, division operations naturally vectorize across them so that we can do element-wise operations without having to do any special trickery like we might have to do in another language, which is very cool. But this is really still only the iceberg of what we can do in APL. And so, like I promised, I want to get to some of these more interesting looking symbols. So we're going to start with this symbol here called the up style. And so we're just going to focus on what is right here called its dyadic definition. And we're going to get to what that means in a little bit. But for right now, we're just going to concern ourselves with what that says, which says we put one element on this side, one element or one array of elements on this side, and one element or one array of elements on this side, and it gives us the maximum. And we get it using backtick S. So for example, if I compare 75.6 and 87.3 using this operation, it will return the max, which is 87.3. And I can do the same thing with this downstyle operator or downstyle function, which is, and there's actually an important distinction between functions and operators in APL, so I accidentally misspoke there, which is backtick D. And so if we do the same thing, it will now select the argument, which has a lower value, which is 75.6. And again, since APL is an array-based language, both of these things naturally generalize to arrays. So if I want to take the maximum in this way, I compare each corresponding element and take the maximum. And in this case, since every element on the right-hand side is greater than its counterpart on the left, we just select the entire right-hand array. And we can do, of course, the same thing with our min operator. So maybe I'll make this a little more interesting this time, just randomly typing things in here. So we took the 1, the 28, and the 2 because for each sort of corresponding pair of elements, those were the smallest. Okay, so now I think it's a good time to address what I was talking about earlier, the difference between monadic and dyadic definitions. And there's actually a pretty simple way to motivate this. So in APL, we only have functions that either take 1 parameter or 2 parameters, which may seem like a very big simplification or constraint coming from other programming languages, but it actually comes from this idea of trying to generalize a very common expression we see in math, which is something like a minus b. We see some sort of operation or function and 2 things going into it. And we also have something we see very often is when we actually have some operation with just 1 parameter going into it. So in the a minus b case, we subtract b from a. In this case, we just turn b negative. So we have this one operation that can either act on 2 parameters or 1 parameter. And it does slightly different things each time, but there's a sort of unifying idea to that operator, to that function. And so APL takes this idea and it abstracts it beyond the simple sort of operations that we see it used in math to build a whole programming language out of this idea. So we're going to consider another very important operator, and we're going to look in turn at its monadic and dyadic definitions, but we'll start with the monadic one. So the monadic definition, or the monadic case, is just the case where it has 1 parameter. So let's remind ourselves that we have this array price, and we're going to use the row function, which is a backtick r, to give us the shape of that array. In this case, because it is a one-dimensional array or a vector, its shape is just defined by one number, 6, defining how many elements are in this vector. And something that's important to notice is that the row operator is a way to generalize the usual command we use to get lengths in other languages, like the length command or the len command, for example, in Python. Because if we look at an array with 2 dimensions, so a matrix, or sometimes called a table in APL, we can use the same operation, same function, sorry, to get a shape for this array. In this case, 4, 6, because we have 4 rows and 6 columns. And that's its monadic definition. We can also use the row function in a dyadic way, which is to reshape arrays. So for example, we see the array forecast has 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So 4 rows, 6 columns, sorry. And that means if we multiply these together, we get it has 24 elements. So we can reshape this array into any other 2-dimensional array whose rows times columns equals 24. So we could reshape it into an array with 12 rows and 2 columns, for example. And the same operator, row, lets us do that in its dyadic case. So before, we just gave it one argument, which is the array we want it to tell us the dimensionality of. In this case, we give it a second left-hand argument, which will tell us what shape we want this new array to become. And now I get an array that is 12 by 2. And this will work with any valid combination, 24 by 1, for example. It will even find ways to make it work if the combination is slightly invalid, though we're not going to get into that in this video. So in this case, we have a 2-dimensional array with 24 rows and 1 column. So it sort of looks like a column vector when we print it out. So row is one of those very bread and butter operations to APL. It's a staple, and we're going to be using it a lot. So it's good to get an understanding of it. Now we're finally going to move to this operator here. And this actually is an operator because, like I mentioned earlier, there is a distinction between operators and functions in APL, but that's a little more advanced. So we'll save it for a future video. But just know that right now, this slash symbol, it denotes an operator. So let's just remind ourselves what the price array looks like. And I'm going to type this. So this is the reduce operator, which is, again, a very essential operator in any functional programming language. And arguably, APL does mix elements of functional programming into it as well, even though it's technically an array-based language. So what this does is it takes whatever function we give it, and it inserts that function between each of the elements of the list. So it takes the first two elements and it applies the function. We get 10.2. Then it takes the result of that and applies it with the function we gave it to the next argument. So 10.2 plus 1.5, 11.7, et cetera, et cetera, et cetera. And we can just think of this as inserting whatever function we designate in between all of these elements. And we can see that that will return the same thing actually. So we would expect it to return 69.6 if how I described that operation is correct, and it actually does, which is good. So again, we can substitute any sort of function in there. We can do reduce with a multiplication, and that just multiplies every element together. For example, we can find the largest element in an array as well using our max function, reduced, because what this does is it compares every element. So first it compares 6 and 2 and says, what is the max there? It's 6. Then it compares 6 and 1.5. What is the max there? It's still 6. Then 6 and 8.9. What is the max there? And now it's 8.9. So it just goes along the array and does this, and it finds that 31 is the max of the whole array. And we can similarly do the same thing with the minimum operation. And now we find that it is 1.5. Okay, so that's a lot of a sort of overview of the stuff you can do in APL. Now let's try and use that to write a useful function or define some useful functionality. So let's take our vector price. And we want to get an average of the vector, of every element in the vector. What is the average value? So how do we calculate an average? Well, given a sequence of numbers, we add everything up and divide it by how many numbers there are. And we just learned that we can add up all the numbers in some array like this. And we also learned that we can get the length or shape of an array like this. So we have the two values we need here. Now all we need to do is combine them in the right way, which is we need to divide them in this case. So let's write out that expression. And that is the average value for the array price. Now, whenever we have some functionality that's useful and we want to reuse, well, we'd like to package it into a function. That's good programming. It allows us to abstract useful features and use them again later without having to redefine them. So let's create a function called average. In APL, unlike in many other languages, we define functions and variables in the same way. So in this case, using the same left arrow or gets this value operator. Now, I mentioned earlier, functions can only ever have a max of 2 arguments in APL. So we don't need to define our own names for the arguments at this point. We realize that, well, we can just set values in the language to either denote the right argument or the left argument, since we don't have to consider as many other cases as there are in other programming languages. So in particular, backtick W omega is used to denote the right-hand argument, and backtick alpha is used to, backtick A, which is alpha, is used to denote the left-hand argument. If there is a left-hand argument, of course, if you're defining a function which is just monadic, then you would just leave it out of your expression. So to denote we're starting a function body, we use double brackets. And now we can just sort of copy this expression in and replace price with, omega. Because omega is going to represent what we pass in on the right. In this case, it will just be our array. So average price. And it gives us the same value. So we've just defined our first function in APL. So another sort of important thing in programming languages, especially with arrays, is not to just be able to add them together and do other operations on them, but to be able to get specific values out of them. We haven't defined that yet. Let's go back to price then. So just like in Python or similarly imperative languages, we get specific values from APL by typing in, using these double brackets as a sort of index function and typing what we want. And APL is also one indexed. So one designates the first element, not the second element, as in many other languages. What's interesting, though, is we can do something like this. So we can pass in multiple elements that we want to get out from whatever array we have. We can almost think of it as passing in a vector of the specific indices we want pulled out. So this gives us the first 4 elements of our array. I could get the first element, the third element, the fifth element, and the 7th element. Okay, maybe there aren't 7 elements. Let's try the first element, the third element, the fifth element, and the sixth element. So this gives me 6, which is the first, 1.5, which is the third, 31 and 18, which are the last two, or fifth and sixth. So this allows us, this is a bit more general, and actually I find it a more sort of clear way to access elements from arrays than we have in other programming languages, because we can very clearly see exactly what we're pulling out from a given array. So let's try and move on to binary data and APL now. And this has to do also with comparison operations like greater than, equal to, stuff like that. So let's look at these two things we have defined. Okay, salaries, which is some vector of the different salaries at some company, we can say, of different workers. So let's say we're interested in all those workers who make above $3,000. So again, the greater than operator automatically vectorizes across our vector. And just to show that it works how we'd expect it in the normal case, 100 is greater than 5, true or 1. 100 is less than 5, or sorry, 5 is greater than, same thing. 5 is greater than 100, false or 0. Okay, now salary is greater than 3,000. So it evaluates this greater than 3,000 for each element and gives us a 1 where that is true and a 0 where it is not. And we can do the same thing with actual and forecast. So let's remind ourselves again, this is an example where we have a vector and we're sort of vectorizing this operation against the scalar across the vector, but we can also take two arrays of the same shape and dimensionality and then match up all their elements and do the same operation. So let's just check intuitively and make sure this does what we'd expect. So for example, in this first position, we get a 0, meaning that actual is less than forecast. 141 is less than 150. How about in this position here, we get a 0, meaning actual is less than forecast again, and 318 is less than 320. So we can verify that is actually what it's doing, matching up the elements and performing the operation. And so we have all the sorts of symbols you'd expect for doing these operations in APL. So obviously you can just get less than, greater than using the shift and the appropriate symbol on your keyboard. To get some of these other, there are also ways to get them using the sort of backtick notation. So we can also get them using, for example, backtick 8 equals not equal. Backtick 4 is less than or equal to. Oops, this is getting covered. Okay, let's see. These, again, you can just get with your keyboard. We don't need a special way to get them. Backtick 6 is greater than or equal to. And that is all the sorts of basic symbols that we use to compare. We also have and or symbols. So and is this upwards caret, which is backtick 0, and or is this downward caret, which is backtick 9. So let's just make sure these work as we'd expect as well. 0 and 0, false and false is false. 1 and 0, false and true is false. But 1 and 1, true and true is true. And in the same case, we have, let's see, 1 or 0 is true, but 0 or 0 is false. We need at least one positive value to get a true value from the or operator. Okay, so now that we've sort of talked about what binary data is, we're also going to see what the dyadic use case is for this slash operator that we discussed earlier. Remember, this operator, which we used as a reduce operation in the monadic sense, also has a operation, a meaningful operation in the dyadic sense as well. So let's look at our price array, I guess. 1, 2, 3, 4, 5, 6 elements. Okay, so now let's see, we want to extract all the elements that are greater than 2. Okay, so we got whether an element is greater than 2, but how do we actually get back the specific elements these correspond to? Well, we can use the dyadic definition of the slash operator. So let's think about this specific example with binary data, because the slash operator actually generalizes beyond binary data, but we'll just consider this example right now. So we think of this almost as a mask. 1 tells the operator, include this in our output list. 0 tells it, don't include it. So we include 6 and 4.2 because those are both greater than 2. However, our mask has 0 at the third element, 1.5, because that isn't greater than 2. And the rest of the elements are, so we have 1s. So this mask says include everything but 0, or include everything but 1.5, because that has a false value since it's not greater than 2. For example, if we have some array like this, and we want to get all, we can just do this again, just as an example. Let's see. All the places where it's less than or equal to 5, maybe. Does that give, okay, that gives us something somewhat interesting looking. And now we can apply this mask back over our initial vector. And so we only get the 4 values with 1s. Those are what we include in our mask. Now, this is a little bit sort of beyond the scope, maybe of just like a quick introduction to APL, but this is something I also think is super cool. So I just wanted to quickly mention it, is that we can actually generalize this idea of the slash operator beyond binary masks. And that happens if we switch perspective from, instead of 1 and 0 telling us include it or don't include it, we think about it on the spectrum. 1 says include it once, 0 says include it no times. But when we think about it in this way, there's actually a meaningful value for numbers like 2 or 3. Those mean include it 2 times or include it 3 times. So let's go back to our price vector and now use a non-binary vector on the left-hand side to the operator. So the 1 says we repeat the first element once, 6. The 2 says we repeat the second element twice, 4.2, 4.2. The 3 says we repeat the third element 3 times. So we have 3 1.5s and so on and so on. So I think this is super cool because, especially when I was first learning this, I was confused how we sort of got from this idea of applying binary masks to using these non-binary vectors. But this happens when we sort of change our perspective from thinking about this as a very absolute sort of thing, whether we include it or not, to a spectrum of how many times do we want to include it, which I think is really cool. Okay, so let's introduce another operator. It's called another function called the Iota function. So it's backtick Iota, and it's equivalent to range. So Iota 100 generates all the numbers from 1 to 100. So also, it may be useful to start working with a new sort of vector other than our price vector. So just give me a moment to load this vector as variable. Now we're going to start playing around with this vector over here. Okay. So for example, what if we want to get the indices where something is fitting to a specific condition? So to make that a bit clearer, what if I asked you get all the specific indices in this array that correspond to an element greater than 35? So let's start with what we know. We know we can get whether or not an element is greater than 35 by applying this operation. And now we know that a 1 represents this element is greater than 35, but how do we actually convert this to a data about indices? So 2, 3, and 5. How do we get that data out of it? Well, let's think about this. So we could use this potentially as some sort of a mask against a vector of 1, 2, 3, 4, 5, 6, 7, right? Because the 0 wouldn't retrieve anything, but the 1 would retrieve, sorry, not 0, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. The 0 wouldn't retrieve anything, but the 1 here would retrieve the 2, and the 1 here would retrieve the 3. So we can use this as a mask against a range from 1 to 7. And we know how to generate a range now with Iota. So what we can do is something like this. So we apply this mask across the numbers 1 through 7. And really, we want to make this a bit more general. How did we know 7? Well, we counted, but we can have APL doing the counting for us with the row function. So, and this is, we haven't really paid attention to it, but now we're sort of in the realm where, yes, we are programming things that sort of look like we're using Egyptian hieroglyphics. We have this very meaningful algorithm, and it's very condensed and terse because we've summarized these powerful concepts into single symbols. So a symbol to represent shape, a symbol to represent counting up a range, a symbol to represent testing an operator, a symbol to represent applying a mask, a binary mask. And oh, I put those in the wrong order because this would generate a range from 1 to 7 and then take the shape. What we want to do is first take the shape, and then actually the 7 shouldn't be there at all. What we should have there is val. So this takes the shape of our array, gets its length, our vector in this case gets its length, then generates a range from that. And then we apply our mask, depending on the predicate on the left-hand side, to that. So here's another thing we haven't talked about yet, which we probably should mention. So we can also deal with strings in APL, and we use single quotes. You can't use double quotes. It's not like a stylistic thing. Double quotes are wrong. We need to use single quotes. So we have analogs to vectors and scalars in strings. Single character, scalar. List of characters is a vector. And so we can do the things we expect with these. For example, we have this phrase, which is a vector of characters. We get specific characters from that using our index notation, like we'd expect. And we can sort of do the same thing we did earlier. Earlier, we wanted to see which the indices of the elements greater than 35. Now we want to see which elements equal A. Where does A occur in this vector of characters? So we can first get that binary mask. Now we know all we have to do. And this is another thing, because we don't do assignment with an equals, our testing for equality function in APL is just a single equal sign. We don't have to bother ourselves with double equal signs like in many other languages, because we have a distinct way to set values, which is the left arrow. So we are creating this binary mask, whether it equals A or not. And then we use our same idea from earlier, where we take the range of the shape. So we're just getting a range from 1 to the length of this vector of characters. And this gives us all the indices where we have an A. And let's just verify that as well. And there's a nice way to verify that, actually, because we can just plug it into our index function, and we should get A, which we do. So we've created this sort of search for an index function. We can also use a different function in APL to test whether a value in one list also exists in another list. So I'm just going to copy this quick example here and replace it with the correct membership. It's called the membership function. So it's sort of like from math, there's that symbol for is a member of the set. This is the same symbol. It's backtick E is what we use to reach it. And so it takes two vectors, and they don't have to be the same shape, importantly. And for each element on the left-hand vector, it says, is this in the right-hand vector? 5 is, 7 isn't, 2 isn't, 8 isn't, 4 is, 9 isn't. And that's how we generate this new binary mask. So we can do this with strings as well, because they are also just vectors. So if we compare the phrases hello world and my name is, and E, the only letters in hello world, which are also in my name is the E at the second position, and the 1, 2, 3, 4, 5, 6. I guess in this case, it would be the space. Is that what it's saying? 1, 2, 3, 4, 5, 6. Yep, the space 1, 2, 3, 4, 5, 6. So the only similarities are the E and the space. Otherwise, they use completely different consonants, combinations of consonants and vowels. So something we can also do, like before, is write a new way to find indexes of something, but in a more general way. So in this case, we might want to give it a particular list of valid strings. So before we were interested, is it equal to an A or not? Now, we may be interested, is it equal to a vowel? A, E, I, O, or U, right? So now we're testing some more complex predicate. We don't just care if it's an A. If it's an A, E, I, O, or U, we want it to return a 1 because that is valid. So now if we want to get the indices of these, we can use the same approach as before using our handy little algorithm. So what did I do? Okay, let me just try typing that again. Iota, row, trace. So this tells us the indices where we have either an A, E, I, O, or U, a vowel. And well, we see in this case, it's only A's and I's. But that is sort of what we were looking for. So this is a lot of the very basic stuff in APL. Two more things I want to quickly go over are the take and drop functions before we call it a day, because take and drop are essential to any functional programming language. So let's define this new list, or actually, let's see, we have val defined still, right? We can just use val in this case. So these are admittedly so far some of my favorite symbols for my favorite symbols in APL, the take and drop up functions, that is. So take and drop are these two arrows here. The up arrow is take, and it's backtick Y to reach it. Down arrow is drop, and backtick U to reach it. So they're take and drop in their dyadic case. So this tail tells us take the first two elements of val, and that's what we do. We take the first two elements. Now we can, sorry, I forgot myself. So backtick U is down. This drops the first two elements of val. So they do opposite things. Here we take the first two elements, and here we drop them. And now, sort of like in other programming languages, if we want to take elements from the back of a list, well, you might try doing something like this. Okay, oops. Have to check again. I didn't know I was blinking. Why? Well, so this is not what we'd expect. It does the same thing as before, it's just negative. And to sort of think through this, we need to try and parse this the way APL would. It does everything right to left. So it first recognizes this, because minus isn't a part of the two, it's its own function, the minus function. And in the monadic case, sorry, it just negates. So first we take the first two elements and then we map a negation operation across them. That's not what we wanted. And so to distinguish between the negation operation and an actual minus number, we have to use this thing called high minus, which we can reach by backtick 2. And it looks like a minus. It's just higher than the typical minus sign. It's raised above to be almost equal with the top of the number. And now it works as we'd expect. We're taking the first two elements from the back of the list. And let's try that again, but this time with drop. Okay, so now we expect to drop the last two elements of the list. So we should have 22, 37, 41, 19, 54, and that is what we get. So this is a very quick sort of fast overview of some of the very basic and cool features in APL. So we looked at how APL is inherently array-based, what that allows us to do, some of those cool hieroglyphic-like operators we alluded to earlier, but this is still really just the tip of the iceberg. So if you found APL to be interesting, and it really is a very cool language, if you've just noticed all that we've been able to do in every case, just a single line, and in most cases, just a handful of characters, it shows you how we can create these very powerful and very terse algorithms and very sort of above normal ways of communicating. We can develop this new, not just a programming language, but a new way to think almost. And that is why things like APL are called tools of thought, because they allow us to think in ways beyond what normal language and even normal programming languages allow us to do. So it's a really very transcendent experience, and it's super cool. So if you've enjoyed this very basic introduction to APL, we hope you'll consider registering for the Paradigm Conference and the APL track, and you can find the links to all that information in the video description. But we're going to be posting these videos weekly, so come back next week for more. And quickly, before we do end this, I want to share with you guys a very cool sort of practice problem that you can use to test your knowledge of APL so far. And this is a problem from Dialogue's APL contest that they hold throughout the summer every year, and it's currently going on now till about the end of July, I believe. This is from the 2020 version, and it's the first problem. So the first problem of the first half, which is the easiest. And so it's asking us to essentially, given some string of DNA bases, which are A, C, Gs, or Ts, count up the ratio of GCs to everything else in that string. So this should be bringing some bells back to the average sort of stuff we did earlier. There's a very similar solution. So you can either refer to this, or I'll leave a link in the video description to where the original problem was posted. but I would definitely recommend trying your hand at this problem and maybe even some of the first problems from other years of the dialogue APL competition, because they're a very great way to test your APL knowledge and make sure you're understanding as well as you think you are. So with that, I'm going to end the video. But if you found this interesting, make sure to check back next week.